So in this video, we're about to prove that the trajectories of the Brownian motion are almost surely nowhere differentiable. There is no point on the typical trajectory at which you can define a tangent to the curve that represents the trajectory. So that is a very strong statement about the lack of regularity of the trajectories, and that rules out standard calculus techniques based on differentiability. Now we're going to prove even more than that. We're going to prove a quantified version of that. So let's have a look at the precise statement, and this is closely related to what we've done in the other direction by showing that the trajectories are almost surely Hölder regular as long as the Hölder regularity parameter is below 1/2. So we're going to define this set G alpha C epsilon, so based on an alpha which describes the level of Hölder regularity, a constant C, and a epsilon that describes the size of a neighborhood. So what is G alpha C epsilon? It is the set of all omegas, or if you want, the set of all trajectories of the Brownian for which you can find a point such that any element t in the neighborhood of that, for any element t in the neighborhood of that point, the Brownian behaves in the neighborhood as a Hölder regular function, right? So we've already proven that if you take C appropriately large, and you take any epsilon, and you take alpha smaller than 1/2, then the probabilities of this set is 1, right? That's the positive result we've been showing. But now we're going to prove a negative result, and we're going to show the probability of this set is 0 whenever alpha is greater than 1/2. That's the theorem here. Whenever alpha is greater than 1/2, all of these sets have probability 0. And that's really going to give us the nowhere differentiability result, because if you think about the set of trajectories that are differentiable at some point s, well, if you're differentiable at some point s, then the ratio bs minus bt divided by t minus s has to have a limit. But if it does have a limit, that means in a small enough neighborhood, it has to be bounded. So if you have a trajectory that is differentiable at some point, then around that point, bs minus bt has to be controlled by a constant times t minus s, at least for if you're close enough to s, so for a small enough epsilon. Now, that means that the set of trajectories that are differentiable at some point is included in these countable unions of g1, j1 upon k, right? If you take the constant large enough and you take the neighborhood small enough, then you're going to have a behavior of bs minus bt. That's what we call Lipschitz continuous. Bs minus bt is going to behave like t minus s as a consequence of differentiability. But that just can't happen because any single one of these sets, as we're about to show, has probability 0, and then you take a countable union. So as a corollary of that theorem, we're going to have the fact that the set of all trajectories for which the Brownian is differentiable somewhere. Now this has probability 0, so the complement, the set of trajectories for which the Brownian motion is nowhere differentiable, has probability 1. Okay, so let's prove this theorem that gives a strongly quantified version of that nowhere differentiability statement. Now the proof of this theorem is not very long, but it's quite nifty. Here's the idea. So the idea is that you take the interval 0, 1, and you cut it into little sub-intervals, as we always do in analysis, and you take them of size lengths 1 upon n for n, an integer, non-zero integer. So what you want to say is you want to say that, okay, if I'm in G alpha C epsilon, that means that by taking n large enough, such that 1 upon n is like epsilon, the Brownian is going to need to have small increments, at least in one of these small intervals. But that wouldn't be enough really to conclude our proof. So the trick is that we introduce another natural number m, and then we're going to have a look not just at one of these intervals, but at a certain number m of them. And then we're going to say that not only are we going to have, if m is large but n is much larger, not only are we going to have the Brownian small in one of the intervals, but we're going to have the Brownian small in m of the intervals. And that's the idea. And this regularity property that we're interested in forces all of the increments to be small in the neighborhood of that point. I mean, quite a few of those increments, if you're doing increments of a tiny interval 1 upon n to be small in that interval, and that's just not going to be possible to have them that small if you force the smallness to be t minus s to the alpha for a large alpha. Right, so that's what we want to exploit, but how do you do that right? You need some properties of the little m and the little n, and how large the little m is and how much larger than m the little n is. So we could run the proof and then find out through the proof what these numbers should be, but that makes it a bit hard to follow the proof. So let me just tell you straight away what we're going to pick. We're going to pick m greater than 1 divided by alpha minus 1/2, which of course we can do because alpha is strictly greater than 1/2. And then we're going to take n greater or equal to m plus 1 divided by epsilon. That means that m plus 1 divided by n will be smaller than epsilon, right? So n would be chosen substantially larger than m, but m will nonetheless be quite large, right? So these are the requirement on m and n, and eventually we're going to send little n to infinity given a fixed little m. Okay, so let me define the key object we're going to show has to be small and then derive a contradiction from that. So we're going to define x and k as the maximum of the increments of the Brownian between a point jn and a point j plus 1 upon n, with j running between k and k plus m. So this is this drawing I had here in green, right? We're really asking for the maximum of the increments. We're going to ask for the maximum of the increments to be small and maximum of these increments running over little m possible choices of such increments. And you can shift that window, that green window that I have here, you can shift it along this interval. And so for k equals 0, you take the first m, and then for k equal 1, you take the next ones, the m elements starting at 1 upon n, and so on and so forth. So we define that. Of course, this is for all k running between 0 and n minus m, right? When you hit n minus m, you're going to take the last little m intervals in these green windows. Okay, so what we want to show, so what we claim, I better keep this information, I suppose, claim the x and k will be very often very small, right? We're going to show that for every omega in g alpha c epsilon, what we have is that there exists a k between 0 and n minus m, such that x and k of omega is smaller than 2 times c times m plus 1 divided by n to the alpha, right? That's what we mean by small. Remember that m plus 1 divided by n is smaller than epsilon, and more importantly, if I send n to infinity, this goes to 0. So this is the claim we need to prove now. How do we do this? Well, let's take a omega in g alpha c epsilon. And then what do we have? Well, we have that there exists an s in 0, 1, such that for all t in 0, 1, whenever t minus s is smaller than epsilon, then bs of omega minus bt of omega is smaller than c times t minus s to the alpha. Okay, that's fine. So now I'm going to pick a k such that this s is somewhere between k over n and at most k plus m plus 1 over n. right? So I just find the right k, the right set of m intervals to which s belong. Okay, now once I've found that k, what can I say for an L in that interval? So for a L between k and k plus m, such that I'm looking inside this green window. So what I can say is that b L over n of omega minus b L plus 1 over n of omega, I can use triangle inequality, right? And I can compare that to b L n of omega minus bs of omega plus bs of omega minus bl plus 1 over n of omega. But what happens now is that our close is L over n to s. Well, it is at most m plus 1 over n away from s. So these things, both of them would have to be smaller, there's two of them, than c times the distance between s and L over n, or L plus 1 over n, which is at most m plus 1 over n raised to the power alpha. And that is true for every L, therefore it's true for the maximum. So what have we? We've proven exactly the claim, right? We've proven that x and k of omega, and for that choice of k that depends on s, is smaller than 2c m plus 1 over n to the alpha. So that proves the claim. Okay, so the maximum of the increments have to be small for all intervals in a set of little m intervals. And we don't know which set of little m intervals, but there exists a k. There exists a set of m intervals such that this happens. So what does that tell us? That tells us that g alpha c epsilon is included in the union from k running between 0 and n minus n of the sets where x and k is smaller or equal to 2c m plus 1 over n to the alpha, right? Now I want to compute the probability of g alpha c epsilon. And what I can say is that it's going to have to be smaller than the sum from k equals 0 to n minus m of the probability that x and k is smaller than 2c m plus 1 over n to the alpha. Now, what is the probability of that? Well, the thing is that this probability here is really independent of k, because increments of the Brownian are independent. So, sorry, not just because they're independent, but because they're IID variables. So really, where it doesn't matter which green window we're looking at, we're going to have all of this probability being the same, and that's going to be the probability that, let's say, the first one is smaller than 2c m plus 1 over n to the alpha. Right, that's because of the IID property of the increments of the Brownian. So IID bj over n minus bj plus 1 over n. Let's put it this way. Okay, but now what does that mean, that xn0 is smaller than 2c m plus 1 over n? Well, again, we're asking now for little m increments of the Brownians to be all small at the same time. These increments are independent. So one thing we can say is that this is smaller than n minus 1, m plus 1. Actually, we can say it's equal. This time it's really using independence of the increments times the probability that the very first increment, which is just b 1 upon n minus b0, and b0 is 0, is smaller than 2c m plus 1 over n to the alpha. And then you have to raise that to, well, how many of them have we got? We've got m of them, right? That's by independence of the increments. Now the good news is that we can compute this probability because we know the distribution of b 1 upon n, right? It's a Gaussian variable, mean 0, variance 1. So this is n minus m plus 1 times 1 upon square root of 2 pi times the integral from, not from minus infinity, because I know that I need to be controlled by this constant. So from minus 2c m plus 1 divided by n to the alpha to 2c m plus 1 divided by n to the alpha, I forgot the 1 upon square root of 1 upon n. That comes from the fact that I have variance 1 upon n, not 1, times exponential minus x squared divided by 2 upon n dx. And all of that is raised to the m. Now I'm going to do something a little simplistic. I'm just going to control this exponential of minus something by 1. That's going to be good enough for my purpose. And I'm also going to control n minus m plus 1 by n. Because what really matters now is the behavior of this quantity as n goes to infinity. So anything that's not a function of n is not going to matter particularly much to the behavior. I want to show that when n goes to infinity, this goes to 0. And then what do I get? I get the square root of n that is raised to the power m. So I get an n to the power m over 2. Fair enough. And then I get I get some constants. So I get 1 upon square root of 2 pi raised to the power m. I get 4c, that's also going to be raised to the power m. And then I get m plus 1 divided by n to the power alpha m. Right, so what is that as a function of n? There's this constant, 4c divided by the square root of 2 pi times m plus 1 to the alpha. All of that raised to the m. I don't care about it at all. It's just some fixed number. C is fixed, alpha is fixed, m is fixed. And then I get n raised to what power? It's raised to the power minus alpha m plus m over 2 plus 1. So okay, does that go to 0? All I need to check is whether or not this number here is negative. And what is this number? Minus alpha m plus m over 2 plus 1. If I would like that to be negative, this is equivalent to saying that m times alpha minus 1/2 is greater than 1. So this is equivalent to m greater than 1 divided by alpha minus 1/2, which is exactly the condition we've imposed upon m. So this entire thing goes to 0 as n goes to infinity. And that tells us that the probability of g alpha c epsilon has to be 0 because it's smaller than this thing. That it's smaller than this quantity for every n, and I can take n arbitrarily large. And that really concludes the proof. And you can see in the proof how important alpha greater than 1/2 is, right? If alpha were to be just equal to 1/2, then this would be just 1. And so we would get that the probability is bounded, which of course it is, between 0 and 1. We wouldn't be able to send things to 0. And then this estimate would be absolutely horrible if alpha were to be smaller than 1/2. Right, and that makes sense because then the probability is 1, so we're not going to get any strong estimate from above on the value of that probability because it's already as large as it can be. Right, so 1/2 is really the threshold, and that's an important aspect of the Brownian, this regularity parameter being having exactly 1/2 as a threshold, so as a threshold of Euler regularity. Now, this plays into understanding more advanced properties of the Brownian and understanding what sort of regularity there is to this madness of extremely irregular curves. But we won't be discussing that particularly much further in the main parts of the course. Although you should keep in mind that this is an interesting phenomenon, because if you were to look at some actual data and ask yourself whether or not the Brownian is a good model for the data you're looking at, you should be looking at geometric properties of the data, things like what we call Hausdorff dimension, related to this parameter here. And if you typically have curves, trajectories of whatever it is you're looking at that are more regular than alpha to the 1/2 or less regular than alpha to the 1/2, then maybe you should use a process that's a little bit closer to that reality of the data. And indeed, this is something that plays a big role in modeling. But for us right now, the one thing we need to really keep in mind is the fact that the nowhere differentiability of the Brownian shuts down any approach to, say, developing an integration theory against the Brownian, which is what we're going to do next, based on standard Riemann or Lebesgue integral techniques. So we're going to need to do something else, and that's called Ito integration, which is the next chapter.